This video is part of the University of Rhode Island's training for the AP Computer Science Principles course. We're going to go over how the Algorithms module in the course works. The Algorithms is Unit 8 in the current instance of the course, and it comes at the end of Quarter 3 of teaching the year-long AP Computer Science Principles course. It comes after they've learned to do programming in JavaScript at the Khan Academy, and the Algorithms module that we uses the Khan Academy material, which assumes they've learned to do the programming in JavaScript at Khan Academy as well. The lesson plan for the algorithms in the Algorithms module calls for 3 weeks, although, as with most parts of the course, this is a recommendation and the pacing of the course is up to the teacher. You can see the learning objectives that we'll come back to, but you can see what we've done is we have chosen from the Khan Academy's full course on algorithms the material that's necessary to get the information that's required by the AP for the AP test according to the learning objectives laid out by the AP. These are the learning objectives for this module. You can see that the AP learning objectives are shown here in square brackets. The AP, in a nutshell, the AP objectives are that the students understand the vocabulary of algorithms, things like intractable problem, unsolvable problem, and that they know basic algorithms. Most probably they'll be focused on the searching and sorting algorithms that Khan focuses on and we chose to focus on here. Not only the algorithms themselves, but most importantly the analysis of algorithms. So things like big O notation, big omega notation, that gives some idea of how good an algorithm is. This is the level the AP is likely to be testing at. The way this lecture is going to work is that I'm going to cover the material in the AP Computer Science Principles course, and I've shown the outline here. And we're going to go down through each one of these, and I'm going to give you the highlights of what you should be covering. The details are in the Khan Academy material, but in an hour or so lecture here, I have to be able to just show you the highlights of it so you get the basic understanding. So we'll go down through them. The first thing we'll look at, the first thing is that there's a 5-minute video that Khan has. It's very kind of entertaining and interesting that you should show the students to get an idea of what an algorithm is, but I won't play that here. The next thing we assign then is a reading from the Khan Academy called a guessing game that works with binary search and linear search. Here is the reading from the Khan Academy, and they have animations in here where the students can try things. Here's the guessing game where you're trying to guess what the number is. So there's a number between 1 and 16 and you have to guess it. And there are different algorithms you could use. Linear search means that you guess 1, then you guess 2, then you guess 3. But if it's going to give you feedback and you know it's sorted, you would probably guess in the middle. So I'll do that, guess 8. And it says the number is higher than 8, guess higher. So a good algorithm would pick in the middle and pick the 12. It's higher than 12, guess higher. So I pick in the middle again, the 14, guess lower, and I get it on the 13. That picking in the middle is called binary search. So there are 2 algorithms that I just mentioned. Linear search means pick this one, then this one, and this one in order. Binary search means pick in the middle, and because you're going to be told higher or lower, then you pick in the middle again, and you keep picking in the middle till you get it. 2 different algorithms to solve the same problem, in this case, guessing a number. The reading makes the point that with 16 numbers, it's not a big deal about which algorithm you choose. None of them will take too much time. But then it goes on to show you an instance of a 300 number game, where if you try linear search, it could take a very long time. But binary search takes a maximum of 9 guesses, and it does a little of the math showing you why it would be 9 guesses. 9 guesses comes from some math, where with 300 items, every time you cut it in half, how many times can you cut it in half? Well, that's log base 2 of 300, which is then rounded down, and then you add 1 to it to get the 9. What we just did is an analysis of algorithms. For linear search of the 300 numbers, where I would guess 1, then 2, then 3, the worst case to get the number is 300 guesses. But if I do binary search, where I first guess in the middle, and then get a higher or lower, and then guess in the middle again, the worst case is 9 guesses. So in the worst case, linear search is 300. In the worst case, binary search is 9. We've analyzed the algorithms and shown that binary search is a more efficient algorithm. The next Khan reading shows an example of an algorithm that's a little bit more robust. Route finding. Like is used in GPS systems that we all use today, and is used in games like Pac-Man, where the ghost is trying to chase down to where the Pac-Man is. So these are things that the students will understand. And the algorithm, for instance, in the ghost example, very similar to what's used in GPS routing, is an interesting algorithm, and they cover it. But very briefly, what it is if this is your goal of where you want to get to, and here's where you start. What you do is you go, and if you have multiple ways of going, you can see there's multiple paths here in the Pac-Man game, and also obviously multiple highways and roads you can go in a GPS routing. What the algorithm does is it goes down and it marks each choice as to how far away it is from the goal. So the first move is here, that's one away. You could either go here to be 2 away or here to be 2 away. If you go here, that's 3 away. If you go here, that's 3 away. So the first pass of the algorithm is to mark what's called the cost. How far away are each of the movements from the goal? Once the cost is computed, then you start at the start and go backwards, and always choose the least cost route. So here we have, we're at 13, obviously we have to go to 12, 11. Then here at 10 we have two choices. We can either go to 11 or 9. So we'll choose the least cost and go to 9. We obviously have to move to 8. We have two choices to 7, but it actually doesn't matter. So we can either go 7 here or 7 here. So let's go here, and then to the 6, the 5, the 4. Now, this way we could go 5, or this way we can go 3. So we choose the least and go to 3, 2, and so that computes the best route from the start to the goal. An example of an algorithm can be good or bad, because there's a least efficient way to do it as well. But the most efficient way is given by the algorithm of computing the cost and then choosing the least cost route back. Now this is a kind of a more involved algorithm, and it's actually quite involved when you get into GPS. So this is not one of the illustrative algorithms that we go in depth with. We use searching and binary search like we just looked at, and sorting, which are more easy to understand. But this just gives the bigger picture that algorithms are very important in things like games and GPS routing. The next con lesson goes on to show what a binary search is, which we already saw with the guessing game, but goes on to introduce what's called the pseudocode. The con reading describes that pseudocode is one way that we use to express algorithms. Pseudocode is a mixture of English spoken language and code, and it's up to the algorithm describer to decide how much English language and how much code to use to get the idea across. So here's the pseudocode for binary search of this list of elements. Let min equals 1, let max equal n, guess the average, the guess that you're going to do is the average of the max and min rounded down. If your guess is right, the algorithm's done and you stop. If the guess is too low, then you set min to be 1 larger than your guess. So if you guessed here the 7 and it said too high, you'd set min to 9 and now be guessing in here. And if the guess was too high, similarly you'd set the max to be 1 less than the guess. And then you go back to step 2 and you keep going until it's right. So this is pseudocode to express the algorithm. The next reading here in con has them do an animation of the linear search and an animation of the binary search, and it restates the pseudocode. But it's doing it with arrays. Arrays are a programming element they learned back when they learned the con JavaScript programming in Unit 7. So they should be comfortable with what an array is. And it's going to show this guessing game, this binary search, and this linear search now applied to an array of numbers in the con JavaScript programming language. So here's the con reading and the animation of linear search. I'll reset it and hit play. And it shows how the algorithm would work on an array of numbers. And you can see this thing called current, which would be a counter that you'd keep in the code, is being moved along or iterated by 1 each time to look at the numbers to see if it's the number that we are looking for. And you can see it has to go through every one of the numbers. Scrolling down, after they explain more of that, there's an animation of binary search. So I can reset it and play it, and it shows that there's a midpoint that you guess, and that the guess is higher, so you move your min, which was all the way over here, you move up to here. And every time you guess, either your max or your min will change until you get it. The next thing the students do is one of the Khan challenges, where they code binary search, and they're going to code it using the Khan JavaScript language that they learned back in Unit 7. This is the Khan challenge in the familiar format that the students got used to back in Unit 7, where the problem is described and Khan gives an outline of the code as a hint, and even gives some of the code where the students have to fill in this do search in lines 7 through 10 with the outline that they're given here. So the students will do this, and there's some coaching that goes on if you get errors wrong, as in all the Khan challenge examples. Here's the solution, and we provide this solution as one of the documents that's in the URI AP Computer Science Principles shared Google Docs, so that you can have a solution that you can use if you need to. But the solution the students have to write is essentially this while loop of, what is it, about 5 or 6 lines here. They write that, and in doing that, they get binary search to work. Now, although the code isn't all that long, you might want to allocate a decent amount of time for the students to do this, because it is coding, and it's coding of an algorithm. You know, for instance, when I first did it, I forgot to add this plus min, and it was a little bit confusing, and I had to think about it a little bit, and oh yeah, I forgot to add the plus min in here. And it took me longer than you would expect to write 6 lines of code, just because of an error of kind of having to think about the algorithm and get the coding to work. The next Khan reading, then, after they've coded the binary search, is to do an analysis of the running time, or the efficiency, of binary search. So the reading explains how to analyze algorithms. And this is probably the most important part of the course and what the AP tests on. And this is their first introduction to it, although they saw a little bit of that in the intro, where we said with 300 numbers, linear search would take 300 guesses in the worst case, and binary search would take 9. This formalizes that, and they talk about how linear search takes n. If n is the number of items, it would take n searches in the worst case, where binary search takes log base 2 of n, and shows here that n increases linearly, where a log function does not even come close to that. So as n gets large, which algorithms on computers typically deal with large data sets, as n gets large, the difference in the runtime, a linear algorithm shoots up, but a log base 2 algorithm stays low in the runtime. So binary search is clearly better, particularly for large numbers, than linear search. And the Khan reading takes them through some of the math and explains that to them. Finally, to end this group of lessons in Khan, Khan actually has some quizzes embedded. So here's a quiz that we recommend you have your students take, where they have to get all 5 problems, and it asks them a question. See, with 32 teams qualified for the 2014 World Cup, if the team names were arranged in sorted order, how many items would it take to do a binary search to find the particular team? And they'd have to understand that it would be basically log base 2 of 32, sometimes plus 1, and so that would be at most 6 would be the correct answer. And the way these Khan quizzes work, if they chose something wrong, it would give them a little hint until they got it right. So you could have your students take it, and part of your assessment would be, you know, do they actually finally get the right answer on the quiz? And even if they didn't get it right the first time, going through the hints probably helps them learn. So these Khan quizzes are a good thing, and we have one here after they've gone through what a binary search and a linear search is, and they've learned a little bit about analysis using n and log base 2 of n. The next group of Khan lessons goes through the algorithm analysis notation, and it gets a little mathematical. You're going to see in the end it actually isn't that hard to really apply this to algorithms, but they do a little math background so that the students who kind of like and need the mathematical foundation get it. They start with a lesson on asymptotic notation. The notion here is that if you measured all the operations of an algorithm, and it came out to be 6 times n squared, n being the number of data items, remember, like n was 300, one of our searches. If the number of operations it took to do whatever algorithm you're trying to analyze was 6 times n squared plus 100 times n plus 3,000. So that's if you counted every operation that the algorithm would do in the worst case. The idea here is with asymptotic notation is that if you look at the factors, the n squared dominates. So this is, as n gets larger, here's n down here, as n gets larger, the n squared part of that equation just takes off. Where here is the 1000n plus 3000 takes off much slower, and as you get out even more data points, it basically becomes insignificant. So what computer scientists do when they analyze algorithms is because computers are so fast, they don't count every term. They count the significant terms. So in something like this, it would really only be the fact that it takes n squared number of operations. And they'll throw out the 6, and they'll actually throw out the 100n plus 3000 and focus on the n squared, because with lots of data items, that's all that matters. And these graphs show it. That's the essence of all of this, is that computer scientists don't count every operation an algorithm does. Because computers run so fast and they work on large data sets, they look at just how the algorithm is related to the number of data items. Is it n squared? Is it just n? Is it 2 to the n? These are the things that we'll see a little later on when we're done here. But this is the essence of this lesson. It introduces asymptotic notation, which essentially means only take the most significant term, in this case n squared. After introducing it, asymptotic notation, the Khan lessons go through 3 forms of asymptotic notation: big theta notation, big O notation, and big omega notation. And each of them are very similar in that they are ways of expressing the efficiency of an algorithm that's kind of crude, not taking into account every operation. Basically, a big theta notation means we can bound the algorithm both on worst case and lower case. Big O means that we only bound it in the worst case, and big omega means we only bound it in the best case. So that's what these 3 things are. So let's take a look at the first lesson, which is big theta notation. Again, big theta notation and all of these asymptotic notations focus only on the important factors. So for linear search, the code has a for loop going from 0 to the end of the array, saying if you found your guess. We know that that's order n, or that's n searches it has to do, because it has to look at every one of them in the worst case. So that the idea is that with big theta notation, the actual runtime is shown here. And that this dotted line means that analysis of algorithms usually doesn't apply to a few number of data elements. So here in the low number of n's, it doesn't really matter what algorithm we use. Remember back in the beginning when we looked at the guessing game with 16 numbers? It didn't really matter whether you did linear search, which is guess 1, 2, 3, 4, or whether you did this back and forth. In fact, with in your head doing a little math, having to figure out the middle, it might have been faster just to guess all 16 numbers. So most analysis of algorithms doesn't really concern itself with low numbers of n, because on very fast computers it doesn't matter. So it starts after this. And the idea is if this is the real runtime of an algorithm, if you counted every operation, the runtime would look something like this curve as n got bigger. But the idea is if you can bound it both above and ahead and below with something that's more known, then you can use that something to express what the algorithm's efficiency is. And this is with a linear bound, and this is actually even a nonlinear bound. But as long as you can say that there's some kind of constant times a function bounding it above and below, then whatever that function is, you can use to say is the efficiency of the algorithm. And we're going to see, for instance, that we say that linear search is order n, or big theta of n, because yeah, it may be more than n. If say n is 300 items in the binary search, maybe it's more than 300, maybe it's less. We don't exactly know or care, but if you say it's on the order of 300, you're getting it close enough. So you're going to see that this order n, and we have other ones, order n squared, order 2 to the n, order log n, it breaks it down to really the 5 or 6, sometimes 10 categories, order n squared. These are what we actually label algorithms with. And that way we don't have to have big polynomials like 6 times n squared plus 100n. We don't have to put that. We don't have to count every operation. We have a kind of concise way of capturing how good the algorithm is. And that works well enough for computer scientists to argue whether the algorithm is good or not. So that's big theta notation, where we can bound the runtime above and below. So here are the primary categories that computer scientists use to rate their algorithms. Order 1 means you get it the first time. It takes one operation to get it. Order log base 2 of n is the next most efficient. And we saw that binary search can be order log base 2 of n. Order n is next, which means that it'll take on the order of one operation for every data item. There are some algorithms that are order n times log base 2 of n. Other algorithms are order n squared. Other algorithms are n squared times log base 2 of n. There are n cubed and some of the others n to the fourth, etc. And the worst algorithms are exponential, which means it's 2 to the nth power. And we're going to see that these algorithms are essentially what we call intractable, because for large values of n, even an extraordinarily fast computer or even parallel computers couldn't solve it in a reasonable time. So that's a bad label down here, and if you can get algorithms that are order 1 or even order log base 2 of n, those are really good efficient algorithms. And we saw that linear search was order n, so that's this one in the kind of third one down, because we had to look at every element. But say we had some other really bad algorithm that went through one for loop to go through every element, but then had some inner for loop that also looked at elements. That would be order n squared, which is down here. So that would be even a worse searching algorithm. So we saw that binary search was order log n, that's a good one. Linear search was order n, and this, whatever bad algorithm this is here, is order n squared. So we have some kind of a rating of how efficient the algorithms are, and those can help us choose the best algorithm to program. As we said, there are three forms of asymptotic notation. There's the big theta that we just went through. The next thing we show them is the big O notation, and then we do big omega. I won't do much on big O and big omega because they're very similar to what we just saw with big theta, just different bounds. Big O basically says the running time grows at most this much, but it could grow more slowly. The this much are the same categories. So it could grow order 1, order log base 2 of n, order n, etc. And so basically the graph looks like this, that after a certain kind of critical mass of points, that the running time will never exceed the bound that we put on there. So if we say it's order n squared, the running time will always be below order n squared. And that's what big O notation means. And computer scientists tend to use big O notation the most, more than big theta and big omega, because they're really only interested in the worst case. How bad could this algorithm be? Because again, computers are so fast, fine-tuning every ounce of efficiency out of it isn't all that important, as long as you know the worst case doesn't take off. So big O notation is pretty widely used. And big theta notation says the running time grows at least this much, but it could grow more slowly. Again, the this much uses the order 1, order log base 2 of n, etc. But we see now here that the running time will stay above the bound that we put in it. So we're basically bounding what the best case time below could look like. So once the students finish the readings on big theta, big O, there are some self-assessments. These are Khan quizzes in here. So here's one and here's another, so that you get a chance to assess. And again, these are nice in that if they get the wrong answer, the Khan Academy coaches them towards the right answer. So that makes up the group of lessons that talks about the analysis of algorithm notation using basically this asymptotic notation of big theta, big O, and big omega. The next group of Khan lessons goes into sorting algorithms. So we've used searching algorithms, binary search and linear search, so far to illustrate, because we could analyze them and saw that linear search was order n, and binary search was better because it was order log base 2 of n. Now we're going to introduce two of the many sorting algorithms. We're going to actually introduce insertion sort and selection sort as the two sorting algorithms, and do a similar analysis on them so students can see that this big O notation, where you throw out all of the constants and things, can work on other algorithms like these sorting algorithms. In the Khan reading is the simulation of a deck of cards, and the students are asked to sort the cards using whatever algorithm they wish. In class, you could actually have cards and hand them out and have the students do that. And they come up with different kinds of algorithms. Some might probably come up with an insertion sort or a selection sort they're going to cover, and they probably won't come up with the more complex algorithms that aren't covered in the AP Computer Science Principles, but are mentioned actually in the Khan material for the students who are interested. So after introducing the notion of sorting, the next thing is a Khan challenge to introduce swapping elements, because sorting usually means swapping. So if I want to swap this 53 and this 2, how I would have to actually do a swap. And if I'm doing that in code to actually sort an array, how do we do the swap? So they take a break and they do some coding here to implement swap, which is a building block that they'll use in their sorting algorithms for insertion sort and selection sort that they build later on in their lessons. So it goes to implementing the swap next. Again, it's a typical Khan challenge where they'll give them the statement of the problem and the outline. And here's the solution. Basically, you're writing a function called swap that takes the array, the first index in the array, and the second index in the array that you want to swap. You declare a temp variable, and that gets the first element of the array. Then you say the first gets the second element of the array, and then the second gets the temp. It basically swaps the first and second elements of the array. And this allows you to swap, like, say, if you were using cards, two cards, but two elements of an array. And again, this is a building block for the sorting algorithms. It's a little utility function that the sorting algorithms will use to swap two elements, because that's what you do when you sort. So with that swap building block, the Khan reading goes into the first sorting algorithm, selection sort, and shows you the pseudocode. Just like they showed you pseudocode for each of the searching algorithms, they'll show you pseudocode for selection sort. Find the smallest card, swap it with the first card. Find the second smallest card, swap it with the second card. Find the third smallest card, swap it with the third card, etc. And you keep repeating until you're at the last card, and at that point the array is sorted. And you should have the students go and do this in the Khan reading where they have an animation. So here we are live in the animation, and we can play it, which shows how you're comparing two cards and swapping them. And you can see how it takes a lot of searches to do this, and this is going to show up when we analyze the algorithm. It's not going to be a particularly efficient algorithm, but it works, and it may be a way that people actually do it themselves when they have cards, because your eyes and your brain are pretty efficient. You don't have to think about the most efficient way to do it. And it keeps on going until this little pointer here, which is indicating that you're at the end of everything up until it is sorted, gets to the end of the list, in which case the entire list has been sorted. Note that in this animation, if you don't want to watch the whole thing go through quickly, the student can single step it. So you shuffle the cards first, and you hit step, and it shows you the first step. So you can think about it, read up here, and then you do the next step. And the student can click through at their own pace this way. So it's good to watch it go through the first time just to get an overall view. But then stepping through it gives you a real feel for what the algorithm does. In addition to the swap that we saw as a building block, the description of the pseudocode for selection sort that we saw in the animation had the code go through and find the smallest or the minimum card so it could swap it back to the beginning. This is actually a little sub-algorithm called finding the minimum of a subarray. That itself is an algorithm that's used in the selection sort algorithm. So the Khan material has them do a challenge where they program finding the minimum element in a subarray. Here is the Khan challenge. Again, they describe the problem, they give you some code, and they give you an outline of the code you need to write. And when you do that, you'll have a new function called index of minimum that will find the minimum element in the array that you can use along with the other function we wrote earlier, the swap function, to have the two building blocks to make selection sort. And here's the solution, which we again put in the AP Computer Science Principles material for the URI course so that you have a solution. Again, I wouldn't give this out to the students, but it's nice for the teachers to have the solution in case they have to go answer student questions. But this is the solution for writing the function index of the minimum. And you can see it's not too many lines of code. It just has to go through and find the minimum element. Once they do the challenge to find this, they move on to actually another challenge. So we have two code challenges in a row where they actually write selection sort. And again, Khan gives them the outline, but here's the solution. So the final solution here is, here's the swap function, and this thing means that the details aren't being shown. But this is the swap function they wrote in an earlier challenge. And here's the index of minimum function, again, details being hidden, but that code is there. So they're asked to write selection sort. And you can see selection sort becomes very easy. It runs a for loop from current, which will be the first element in the array, to the end of the array, incrementing current. Calls find the index of the minimum in the array, and swaps the index with the beginning of the array. It then increments current, which will say the first element in the array is now sorted. Go find the index in the rest of the array and swap it into the second position over and over and over again. So the beauty of writing the little utility functions of swap and finding the index, which is in of itself is kind of a sub-algorithm, by having these two written, selection sort is a for loop with two calls in it. Very simple, pretty easy to understand. And again, this is the solution for you, so you know what the solution is. The students should do the Khan challenge and come up with this on their own. The Khan reading now goes through the analysis of selection sort. It's going to come up with one of those labels, order n squared, that we saw back in the notation using big O. Well, they'll use big O, but it could be big theta or big omega, but one of those notations. So the reading takes them through kind of a detailed analysis, but the essence of it is that you can see the for loop of selection sort runs the entire length of the array. That's n times. But inside it's calling min, index of min. That actually runs through the array up to n times, and it keeps running smaller and smaller. So basically if you look at this, it's the outside for loop runs n times, calling this, which has its own little for loop that runs up to n, then n minus 1, then n minus 2 times. That becomes what's called a series, and doing a series analysis of n times n minus 1 times n minus 2. From mathematics, the series analysis says that essentially n squared over 2 plus n over 2. That math is covered a little bit in the Khan reading, but it's really mathematical. In a math class, they have to learn about series and how the bounds on series. But using that bound on series, this n squared over 2 plus n over 2 that comes out of how many times each for loop runs, if you look at this and apply what we learned back in our notation, n squared is the dominant term. We don't care about over 2, and we don't care about this essentially constant term. It's n squared. So we see that selection sort is order n squared. And this is the level of analysis that computer scientists use. Just look at the for loops, kind of figure out that it's a series, and you kind of have to know the series in this case comes out to be n squared. And this is the kind of thing that the level they're going to test on the AP. They wouldn't expect the students to actually do out series math, but they should be able to look at it and say it's a for loop, and inside there's this called index, which itself runs a for loop, so that's order n squared. It's running through n, and then each time you do an n, you have to run through n each time, and that's order n squared. So that's the level of analysis. The reading does more detail, but again, part of the computer science analysis is to remove detail and not necessarily have to get into the formal series analysis math. Just look at the for loops, say how many times it runs, and say that's an n squared algorithm. So after taking the students through the first sorting algorithm, which was selection sort, we show them another sorting algorithm called insertion sort. So again, they can compare the efficiencies of these two algorithms that basically solve the same problem, sort an array. Insertion sort is actually pretty easy to understand because it's what most people would do if you were dealt a hand of cards all down by the dealer, and you pick them up one at a time and you wanted to keep the cards sorted in your hand. Very typical thing to do when playing cards. The idea is that you would pick up a card, put it in your hand, and you'd pick up the next card, and if it was left, you'd put it to the left in your hand, and if it was right, you'd put it to the right, and you'd find the right position to put it into. That embodies the idea of insertion sort. There is an animation in Khan that shows insertion sort. So here in the Khan reading for insertion sort, we show that there's one card in your hand that you've picked up. You click next step, and you see that next card is a 6. Where do you put it? You say that you look at what you currently have, which is a 7, so you're going to put it to the left of the 7. So the animation takes you through that. Then you pick up your next card, you look at it, you see where does it go in the current sorted order you have in your hand, and you put it in the right place. Pick your next card, okay, and it'll take you through all the way looking at each card, and that is the insertion sort algorithm. We can see here on the slide, in an array it's similar, but you keep some pointer or some index into your array saying what's sorted so far. And one element by itself is sorted, so far the 10 is sorted. Then we look at the next element, which is the 7, and put it in its sorted order, which is before the 10. We can see that here. So now 7 and 10 are sorted, and we're looking at the 3. Put the 3 in. Now 3, 7, and 10 are sorted, we're looking at the 13. And it goes all the way through until sorted is the entire array, and we stop. That's how insertion sort works. Now if you follow the Kahn material, they have them program insertion sort by first implementing a little utility function called insert that'll stick it in the right position, and then insertion sort itself. But again, we only have 3 weeks allocated in the AP Computer Science Principles course, and coding takes a long time. They got some coding experience with selection sort up here, doing the Kahn challenges. We recommend that you skip the Kahn challenges here in the interest of time. But if you have time, or the students are interested, they can go do the challenge. But after implementing the insert function, if they choose to do it, then Kahn gives them the pseudocode for insertion sort. And you can read through the pseudocode here. Insert into the, call insert, which is the little function you just wrote, to insert the element that starts at index 1. And it kind of talks you through the algorithm for insertion sort, which actually looks a little bit more complex here in pseudocode than it does in real code, as we'll see in a few moments. But it talks through, in pseudocode, the algorithm for insertion sort. And again, that most of us intuitively do this with a hand when we're dealt cards and have to do keep our hand in order. And again, we recommend not having the students do the challenge, but you might want to show them the code. And this is the solution to the Kahn challenge. Because insertion sort is actually very little code. Here's the utility function, insert, that they actually wrote in the previous challenge, this challenge here. You can see it's a for loop that just shuffles things and puts the elements in the array. Once this is written, here's the insertion sort. Give it an array, and it'll shuffle the array around. How? It calls a for loop to go through the array, inserting the elements in the array. Very short code, just a few lines here and a few lines here to do all of insertion sort. Short, elegant code. Now that the students understand insertion sort and have seen the code for it, we can do our analysis using our big O notation of insertion sort. So if you look at the code, in the worst case, let's do a worst case analysis first. In the worst case, we have to loop through every element in the array, and every element in the array is doing insert, which has its own for loop, which has to go through every element in that subarray. So in the worst case, it's a for loop, calling a for loop, and that becomes order n squared. So in the worst case, insertion sort is order n squared. If you remember, selection sort was also order n squared. But in the best case, if the array is already sorted, insertion sort finds that with one pass. So in the best case, insertion sort is order n. Whereas selection sort still has to do all of the shuffling, so in its best case, it's order n squared. So we can see between insertion sort and selection sort, in the worst case, they're both order n squared. But in the best case, insertion sort wins because it's only order n. In the average case, both in selection sort and insertion sort are order n squared. But if you're really getting picky about it, and again, computer scientists usually don't do this, if you look at those constants we threw away, the constants are actually significantly bigger in selection sort than they are in insertion sort. So in general, insertion sort is considered a better algorithm than selection sort, because insertion sort has a better best case and a better average case, even though in both the case of insertion sort and selection sort, they're order n squared in the worst case. So insertion sort is usually considered a better algorithm. Now there are even better algorithms that are covered in the Kahn material, things like something called quicksort, bubble sort. There are others, but those are what are called recursive algorithms that are beyond the scope of what we're teaching in AP Computer Science Principles. But there are multiple different sorting algorithms. All of them can be analyzed using this order notation to find out which one is the best. But if you only had 2 choices of code between insertion sort and selection sort, you'd probably choose insertion sort. And its code is actually pretty clean and short, so it's not a bad sorting algorithm to have handy. This concludes our discussion of algorithms and analysis of algorithms. There's one part left in the material for AP Computer Science Principles that talks about the limitations of analysis of algorithms, and we'll get into that next. The final topic we're going to have the students learn is the limitations of algorithms. And this is learned not from the Khan Academy, but from a nice video lecture done from Trinity University, which is about 11 minutes, a little over 11 minutes long. And it covers pretty much, it was actually done for AP Computer Science Principles, and it covers pretty much what they need to know for the limitations about undecidable, unsolvable problems. The essence of this video lecture, so you can see it in a few minutes instead of the 11 minutes, is it defines intractable problems and undecidable problems, or unsolvable problems. Undecidable and unsolvable are similar, to the point where we can use the terms interchangeably. So intractable problems means that the problem can only be solved by inefficient algorithms. It's solvable, but the only algorithms are inefficient. For instance, many of the intractable problems are labeled as order 2 to the n. Not even order n squared, those are fine. They're not great algorithms, they're fine, but anything that's order 2 to the n basically means it's exponential, and as n gets even moderately big, the number of operations have to be done explodes to where it's intractable, which means it really can't be solved in a reasonable amount of time. Some examples of this: brute force decryption, where if you've encrypted something and the computer wants to try all possible combinations, say to try and find your password, tries A, AB, tries all possible combinations. If you have a reasonably large password, then the brute force becomes intractable. This is why banks have you have your password over 8 characters long, drawn from several alphabets, because it becomes intractable. Too many combinations for the computer to try. So brute force decryption is an intractable problem. And that's actually a good thing, because we can use encryption to keep our things private. So the fact that there aren't any good brute force decryption algorithms that aren't intractable is a good thing. Another example of an intractable problem is the traveling salesman problem. The traveling salesman problem is essentially this. A salesman has a list of cities that they need to visit and wants to find the shortest route to visit each city where each city is only visited once. Kind of practical problem. It turns out to be intractable to try all possible combinations of going to cities. It's solvable. You can do all possible combinations. It's just that if you have a decent number of cities, it takes way too long to compute what the shortest route would be. For many intractable problems, computer scientists don't use an algorithm, which is trying to find the best way to get, for instance, to all the cities in the shortest amount of time. Instead, they use something called a heuristic. A heuristic is like an algorithm in that there's a step-by-step set of steps to go through to do the solution, but a heuristic doesn't always solve the problem and doesn't always solve it in the best way. But it does it enough times, or it's good enough that you can use it, because doing it the best way would take way too long. So traveling salesman problem, for instance, is often solved with a heuristic where they go to the nearest city first. And that works a lot of the time. Isn't always the most optimal, but it's easy to compute, and the optimal would take way too long. So again, intractable problems, the algorithm or the best solution takes way too long, often order 2 to the n kind of computations. Either we just say we can't do it, which is most brute force encryption or decryption on big passwords, or we use a heuristic which solves it close enough. The other thing covered in the lecture and required by the AP to understand is something called undecidable or unsolvable problems. And there are some problems that simply can't be solved by an algorithm or a heuristic. And it talks about one called the halting problem. And the halting problem is detailed in the video lecture, so I won't detail it here. But essentially, it says, can you tell if a computer program will halt given an arbitrary set of inputs? And again, that's a very esoteric description of a problem, but it's the classic one used to describe unsolvable problems, and the 11-minute video lecture does more detail on it. Really, for the AP Computer Science test, knowing that the halting problem is an example of it, and that there are unsolvable problems, is probably the level they need to know. Unsolvable problems involve kind of difficult mathematical proofs to prove something's unsolvable, which is beyond the scope of the AP Computer Science Principles course. But understanding the vocabulary, that there are unsolvable problems, and that something called the halting problem is an example, is a good level of knowledge for the AP test. This concludes our description of the material we've put forth for you to teach what's required on the AP Computer Science Principles. We've picked material mostly from the Khan Academy, and we've picked the material that we think kind of gets the idea across and hits the learning objectives that were laid out by the AP, as you can see here. Develop an algorithm to implement. So they learned how to do algorithms for search and sorting. Express an algorithm in a language. We showed it both in pseudocode and in a programming language with Khan. So they've learned both of those. Explain how programs implement algorithms. So we saw code that implemented binary search and code that implemented selection sort. Explain the difference between the algorithms that run at reasonable time and those that don't run at reasonable time. That was that last slide talking about intractable things and how we have to use heuristics sometimes. Explain how algorithms use, different algorithms solve the same problem but have different efficiencies. We saw two examples. Linear search was less efficient than binary search. Selection sort was, at least in the average and best case, less efficient than insertion sort. Explain the difference between solvable and unsolvable problems. That was the last thing we talked about, that the halting problem is unsolvable, and unsolvable problems basically mean there is no algorithm to solve it. Explain the existence of undecidable problems in computer science. Pretty much the answer to that, there's many answers, but the answer they're expecting is an instance of the halting problem, which again is described in the video lecture in some detail. And evaluate algorithms analytically and empirically for efficiency. And we did that. That's the whole order n squared, big theta, big omega. That addresses that learning objective. Now this is challenging to fit into 3 weeks, particularly with some coding in there that can take some time. So you do your best to pace it. If necessary, you might allocate more time. Maybe you can, if you have experienced programmers, do less in Unit 7, so they don't do quite as much programming, but they just spend more time in algorithms. At this point, we still don't know exactly the level the AP is going to be testing at on algorithms. This is the level that meets their learning objectives. And it's a good, solid introduction to algorithms that students will learn at the college level. This kind of stuff at the University of Rhode Island is in our second semester freshman course. We do a lot with this kind of thing. We have basically a course in algorithms with some analysis of algorithms. And then in their senior year at the university, they actually do a whole mathematically oriented course in the analysis of algorithms. So this module is a good introduction into algorithms and the analysis of algorithms, and we believe is sufficient for the AP Computer Science principles.